In this video, I'd like to talk about the powers of the imaginary unit. And before we look at any specific problems, let's think through what the different powers of I are, or what the different powers of the imaginary unit are. Since we call the imaginary unit I, and remember I is the square root of -1. So there are no real numbers such that when you multiply them by themselves that give you -1. Mathematicians came up with a symbol to denote a new type of number. This is called the imaginary unit. And remember, don't get too caught up on the word. You can think of these numbers as rotational numbers. And in the next video, when we talk about the geometric interpretation of these powers of the imaginary unit, it will make a little bit more sense why you can think of these as rotational numbers. Or, like one of the greatest mathematicians in history, Carl Gauss, liked to call these are often referred to as lateral numbers. So, before we look at those geometric interpretations, let's just think this through algebraically. So, we know that when I is raised to the first power, we just refer to it as the square root of -1. And when we square I, what we're going to get is the square root of -1 squared. And when you square a square root, they cancel each other and you just get back -1. And it might help to just think of an actual example with real numbers here. So let's say we had the square root of 4 and we square that. Notice that if we take the square root first, the square root of 4 is 2, since 2 times 2 is 4, and 2 squared is just 4. So taking the square root and then squaring, those are inverse operations. They cancel each other out, just like multiplying by 4 and then dividing by 4. So you just get back what is on the inside of the square root here, just like we did here. So that's why we got -1 here, since the square root and the square cancel. Now, with these two pieces of information, we can figure out what I to the third power is, and I to the fourth power, and so on. And we're going to notice a pattern. So I to the third, what we can do is essentially just use exponent properties. Since we know that when we take I squared and we multiply it by I to the first power, that this is equal to I to the third power. Since remember, if we have, let's say, x to the a power multiplied by x to the b power, when you have the same base, you can just add the exponents. So we're just applying that property in reverse. We're starting on the right-hand side and going backwards. But you can see that this is true since they have the same base, and we can just add these two exponents to get to 3. Now, the reason we do this is that we know what I squared is, and we know what I is. So I squared we know is -1, so let's just replace that. And I, we will just leave that as is. You could write it as the square root of -1, but typically the square root of -1 we will just write as I. So we have -1 times I, which is just -I. So I to the third power is the opposite of I. Then we'll go to I to the fourth. Now I to the fourth, we can use this same idea, except break it into I squared times by I squared. And we know I squared is just -1, so this is -1 times -1, and -1 times -1 is +1. Now, these 4 powers of I, these are the primary powers. And essentially every power after that is going to be one of these 4. So let me make a little bit of room. And when we look at I to the 5th, what we're going to see is that we just get back one of these 4. So I to the 5th, we can pull out an I to the 4th. We can use that exponent property again. So it's I to the 4th multiplied by I to the first power. But I to the 4th, that's just 1. So you get 1 times I, which is I. So I to the 5th power is just equal to I. And let me delete this, and then we can keep going. So let's now look at I to the 6th power. We're again going to pull out an I to the 4th, since we know that's just equal to 1. And we would also have an I squared, since if you add the exponents, you get 6. Now I to the 4th we know is 1, and I squared we know is -1. So I to the 6th is -1. Or in other words, I to the 6th is just equal to I squared. Whereas again, I to the 5th was equal to I. If we keep going, we can look at I to the 7th, but you might see the pattern now. And we're going to pull out I to the 4th and multiply that by I cubed this time, since those add up to 7. Now I to the 4th we know is 1, and I to the 3rd is just -I. So I to the 7th is simply -I. It's the opposite of I. But again, notice that it's the same value as I to the 3rd. And lastly, if we do I to the 8th, that really is just I to the 4th multiplied by I to the 4th. And each of these are 1, so you get 1 times 1, which is just 1. So I to the 8th power is the same thing as I to the 4th. And if we did one more, you'll see that we're just going to repeat the cycle again. So if we look at I to the 9th, that's really just I to the 4th times by I to the 4th. Or you can even write this as I to the 4th squared. And then we're going to multiply that by I. So this is really I to the 8th. When you have an exponent to an exponent, you're going to multiply, and that comes from this exponent property. Exponent to an exponent, you multiply. And so this is I to the 8th, this is I to the 1st, and those would add up to I to the 9th. And so I to the 4th we know is 1, so you get 1 squared multiplied by I, but 1 squared is just 1. So this is just I, and you can see that's the same thing as I to the 1st power or I to the 5th power. And I to the 10th will be the same thing as I squared, I to the 11th would be I cubed, and so on. So essentially, these go in a cycle of 4 different values. So the key to solving problems where you have I to some different power is to figure out which part of the cycle that it's actually in. So let's say we have I to the 23rd power. And the simplest value in the cycle is I to the 4th, since that's just equal to 1. So the approach to solving this, to figuring out what this is equal to, which one of these 4 values, is to essentially figure out how many whole times 4 goes into 23. And 4 will go evenly into I to the 20th, since that's just 4 times 5, and you would have 3 left over. So another way to write that, I to the 20th, that's really just I to the 4th, and you would have that 5 different times. Now you could write out I to the 4th, I to the 4th, I to the 4th, I to the 4th, and I to the 4th times I cubed, or you can just raise it to the 5th power, since those mean the same thing. And then we have I cubed here, and I to the 4th, like I mentioned, we know that's just 1. So you have 1 to the 5th times I cubed, and 1 to the 5th is just 1, and I cubed we know is -I. Or if you want, you can even break down I cubed into I squared times I. So really, you just need to remember these 2 values, and you can rederive the rest of them from those 2. But we know I squared is -1, so this just is -I. So I to the 23rd, since we just ended up with an I cubed after we pulled out all of the I to the 4ths, this is -I. So that's the approach for solving these problems. You just need to figure out how many whole times 4 goes into whatever your power is, and then see what you have left over and deal with that accordingly. So for this particular example problem, I to the 8th, well, that's just I to the 4th times by I to the 4th, and I to the 4th is 1, so you get 1 times 1, which is 1. So choice letter A would be the correct answer, and of course we did solve that down here as well.